In this video, we're going to look at the theory behind differential equations, why it is that things work the way that they do. And it all comes down to linear algebra. In the end, linear algebra determines everything that happens in calculus. It doesn't seem that way when you first begin an engineering degree and you're told that you're going to have one linear algebra course in the fall, and that's it. While in calculus you've got Calc 1, Calc 2, most of the departments have a Calculus 3, all of the departments have something that has to do with differential equations, numerical methods usually has to do mostly with calculus methods. It just seems like everything is calculus and there's just a little bit of linear algebra. But what is really happening is that linear algebra determines everything else that happens within calculus. So here's a rough idea of how this works and why. When we look at the derivative, if I wanted to take the derivative of the sum of two functions, then this is just the derivative of the first function plus the derivative of the second function. So far so good, nothing interesting, nothing we don't already know. If I take the derivative of a constant times our function, the constant sort of comes out, right? And you can write this as c times the derivative of just f of x. And when that's all you write, those are two rules that every calculus student has branded onto their brain. They know this incredibly well, and it doesn't tend to be thought about. It's the summation rule, and it's the constant multiplier rule. Hopefully you don't have a name for it, you just know it. But in linear algebra, what we had is that if you take a linear transformation, let's call it t, and you apply t to the sum of two vectors, then you can apply the linear transformation to each one separately and add the results after the fact rather than before. Same thing with constants. As a matter of fact, this is the definition of a linear transformation. A linear transformation is one which obeys these two rules. Multiplying by a matrix is definitely a linear transformation. It obeys these two rules. Well, so is taking the derivative. Even though the functions themselves are not linear, the operation is a linear operation. When we take a derivative, you can break up the addition, you can take out a constant multiplier. And so all of the rules that we learn about linear transformations also apply to the transformation of taking a derivative. Things look a little bit different because the spaces that we work with in linear algebra, within engineering, within first-year engineering certainly, are all what we call finite dimensional. We work with r to the n, and that's it. We don't go beyond that. The space of all the possible functions, that one has an infinite number of dimensions. It's actually a very large infinity. There are a lot of really weird things that happen in terms of the theory if you want to get into it. I find them absolutely fascinating, but they kind of require you switching over to doing a math degree, which is a good thing. There's a lot of excellent stuff within it, but it's not what I'm being paid for. So let's stick to what we have over here. We're going to look at linear transformations. One of the things about them, one of the most important factors, is this thing that we call the null space. The null space of a linear transformation is the set of all vectors such that when you take the linear transformation and apply it to your vector, you get 0. So it's everything that the linear transformation sends to 0. And in particular, this thing right here, this is a subspace. Right, so it has all of the properties of a subspace. You can find a basis for it, you can find its dimension, you can do all of these wonderful things. Well, if taking the derivative is a linear transformation, then it has a null space. We can find the set of all vectors only in calculus we call them functions, that gets sent to 0. So this is a set of all f of x such that the derivative of f of x is equal to 0. Now, I want to imply that it's equal to 0 throughout. It's equal to the 0 function. So equal to 0 for every x. This is the notation that is usually used. Right? We often refer to it as equivalently equal to 0 or always equal to 0. There are a number of ways of reading that particular symbol. So this thing over here is something that if you ask a class of calculus students, what is this equal to? Once they get over the fear of the word null space over here, if you look at just the definition over here, what are these functions? You will get the correct answer. You will get that it is every function f of x, where f of x is a constant. Well, that's certainly true in one direction. Every function that is always a constant definitely has its derivative is always 0. To go in the other direction is a little bit difficult. To demonstrate that there isn't anything else, we have to go to the mean value theorem. And if you check out our videos on the mean value theorem, we do actually go through this and we explain why it is that this is the set of them. But we can go one step further. Let's do this. Let's see how frightening we can make it. We'll take a particular function. Let's take this. Let's let g of x be the function that is always equal to 1, the constant function that is always equal to 1. Then what happens? Every function over here, every function that is always equal to c, what is that? That's just c times g of x. Okay, so therefore, for every f of x which is always equal to c, we have f is equal to c times the function g. And so the null space of the derivative is just equal to the span of g of x. We have a basis for that, which means that the null space has dimension equal to 1. And that's why when we take a single derivative and try to solve a first-order linear differential equation, we know that having taken a single derivative, we have some operation with a null space of 1. We are trying to undo it. Right? The solution doesn't have a derivative in it. So we're trying to undo a derivative, so we expect there to be 1 degree of freedom. We expect there to be something of dimension 1 as our solution. And indeed, in the first chapter on differential equations, everything, say we started with y prime is equal to a times y, we end up with y is equal to some constant times e to the ax. This is the span of e to the ax. As long as we're solving a homogeneous system, we are going to get a subspace as our set of solutions. In second-order differential equations, what happens is that we take the derivative twice. And so the dimension of the null space for each application is equal to 1. And so when we take a second derivative, we are sending 2 dimensions to 0. When we undo it, we expect to have, when we're trying to solve any of these equations, we expect the solution to be c1 times some function plus c2 times a second function. It is the linear combination of these two linearly independent vectors. How do you prove that they're linearly independent? How do we know that we've got exactly the right number? Those are significantly more complicated details, and you will get them in your your differential equations course in second or third year. But at the very least, you should have a sense of why this thing happens.